and welcome to NPTEL MOOC on Fiber-Optic Communications Systems and Techniques course. In this module, we discuss boundary conditions and reflections from perfect electric conductor. Now, before we discuss boundary conditions and whatever the reflections from a perfect electric conductor, let us go back to our childhood and look at some of the experiments that we would do without really knowing that they were experiments that involved light. So, for example, I have a glass of water here, okay, and then what I have done is that I have kept this pen at a angle, of course, because the cup cannot hold the pen at any different angle. So, I have just kept it like this, and if you focus a little bit onto this one, you will see that so if you look at it from the top, of course, you can do it at home in a matter of a minutes. You just pick up a glass of water and then put the pen inside that water, and what you see is that this appears, the pen although is straight and has no discontinuities, it appears that the pen is actually bent. If you look at it from my perspective, what I am holding, you will also see a reflection of this pen coming from the bottom, and then it is actually on the top layer of the water. So, you can see double reflection, so to speak, but the primary thing that we have all observed in our childhood is that if you dip a pen here, although the pen is supposed to be straight, the pen appears to be bent. It appears that the pen is actually kind of displaced in the water and is appearing at a different direction. So, we have seen these phenomena, maybe we have also tinkered with these different angles and then observed how this bent inside the glass would look like, and we have done it without really knowing what causes all this type of a phenomena. It turns out that this phenomena that I just showed you, okay, and there are a lot of interesting things that you can do it for yourself. So, I would suggest that pick a clear glass of water and then put a pen and then actually follow what goes on to the kind of angles that you would see, and then twirl the or twist the pen around, turn the pen around, and then you can see how as you change the angle at which you keep the pen inside the water, the corresponding the image in the water itself also changes, or rather the part of the pen in the water also changes. So, all this we have seen, and this goes by the name of reflection and refraction phenomena. Reflection is when you stand in front of a mirror and you are able to see yourself, that is reflection, and when you do experiments like the one that I demonstrated at the beginning of the module is what is called as refraction. Sometimes this is also called as transmission. So, it seems that whenever light enters from one medium to another medium, in the example that I showed you, the medium where the light was initially propagating is definitely in the air, right, and then the other medium to which we have looked at is the combination of water and glass. So, water is a second medium. So, whenever light goes from one medium to another medium, you expect two things to happen. One is partial reflection. So, the entire light would not be reflected unless you specifically create conditions for that to happen. So, there will always be just about partial reflection, and there is also partial transmission into the second medium, right. These observations are not new, of course, these observations have been going on for thousands of years, but it was Snell who first formulated some quantitative laws that connects this reflection and refraction phenomenon, right. He specifically considered the following situation. So, you have this blue line here indicating the interface between two medium. So, as I showed you, one medium is air, the other medium is glass, for example, or it could be water. I have written glass here, but the same kind of ideas apply everywhere, right. So, we had light represented in the form of a ray, but because you have looked at or you have listened to the last module, you perfectly know that light is not just composed of a single line that we would call it as a ray, but also these red lines which are all the constant amplitude fronts, along which you will have electric field, and perpendicular to both these electric field as well as the direction of propagation would be the magnetic field. So, light is actually a wave, but for our application or for our consideration in this first few minutes, it is sufficient for us to consider light as a ray, and then we know that, right. So, when light is incident to the second medium at an angle theta 1, then there is a partial transmission into the second medium where the light makes an angle of theta 2, just like pen dipped in the water would seem to have an angle theta 2 with respect to normal to the interface, right. So, with respect to normal to the interface, there is an angle theta 2 and there is a partial reflection as well, and the reflection angle would be denoted, in this case I have denoted it as theta 1 prime. Okay. What Snell observed was that the angle of reflection, which is theta 1 prime, is exactly equal to the angle of incidence. So, this is called as the first Snell's law of reflection or first Snell's law, and this pertains to reflection. Okay. And the second law that he formulated, okay, by lot of careful experiments, was that the amount of angle theta 2 that the ray into the second medium makes with respect to the normal actually depends on several parameters. It depends on the refractive index of the medium, not only of the second medium, but also of the first medium. So, in fact, the law goes like this: n1 sin theta 1 will be equal to n2 sin theta 2, where n are the refractive index of those particular media. So, for medium 1 it is n1 and for medium 2 it is n2. Okay. So, you can use this equation to calculate what would be the angle theta 2, you can use this equation to know what is the angle of reflection, and as you change the angle of incidence theta 1, this is theta 1 is the angle of incidence, the corresponding angle theta 2 also changes, right. There is also a certain specific case where you might end up having a following scenario. So, for example, if I somehow make sin theta 2 equals n1 by n2, right, then what will happen? If I make sin theta 2 equals n1 by n2, then Snell's law tells me that n1 sin theta 1 will be equal to n2, or rather I am sorry. So, if I try and make sin theta 1, not theta 2. So, if I make sin theta 1, which is the angle of sine of angle of incidence, into something like n2 by n1, right, then what I will have, what will I have is n1 times, since it is sin theta 1 and we have just made sin theta 1 equals n2 by n1. So, this becomes n2 by n1, and then you have n2 sin theta 2 and n2 cancels on both sides, and then what you have is sin theta 2 equals 1. Because theta 2 can be at most from 0 to pi by 2, correct, because 0 corresponds to propagation along the normal and pi by 2 corresponds to propagation at 90 degrees to the normal. So, what this equation is telling me is that theta 2 can be equal to pi by 2, which means that the ray, instead of being transmitted into the second medium, actually starts to travel parallel to the interface, and this phenomenon where the angle of incidence is chosen in certain manner, which is given by this expression, such that the corresponding transmitted light propagates parallel to the interface, is called as total internal reflection. Okay. So, this phenomenon is called as total internal reflection, and this angle at which this total internal reflection just barely is possible is called as the critical angle. Okay. Now, observe certain thing. In this sin theta 1 equals n2 by n1 expression, is it possible for n2 to be greater than n1? It is not possible for n2 to be greater than n1, because in that case this right hand side will be greater than 1, and we know that real solutions of sin theta can never be greater than 1. So, if you plot sin theta, you would see that the limit on sin theta is always plus 1 on the positive side and minus 1 on the negative side. So, it can't go beyond that. So, clearly total internal reflection cannot happen when the incident medium has a refractive index which is less than the medium to which we are trying to, or to which we have incident the light. But the other situation is possible. So, I can always have a situation where n1 is greater than n2. Okay. In this case, theta 1 will have a real solution, which means that one of those angles becomes the critical angle for which the ray of light actually propagates parallel to the interface. So, total internal reflection phenomenon happens only when n1, which is the medium of refractive index of the medium or the incident medium, is greater than the second medium. Okay. So, this is a fundamental condition for total internal reflection. We have talked about all these angles, reflection, refraction phenomena, but if I were to ask you how much power is actually reflected when light is incident, and is that the only thing that happens, is it also possible for us to look at the phase of the light upon reflection or phase of the light after transmission? Is it possible for me to have light totally internally reflected and if that is happened, if that happens, then what will happen to the fields on the second region, or the medium 2. These kind of questions cannot be answered by the simple picture that we have so far considered, the simple picture being that of light rays, right. So, in order to answer these questions, it is necessary for us to look at the electromagnetic nature of light, and that is what we are going to do. So, what we actually have is the following scenario. So, I have a certain interface. So, this is how I just represent an interface, and this is a very specific kind of an interface. This is called as an abrupt interface, meaning that this is a idealization of an actual interface that would happen. I mean, in practice you would not have a scenario where the medium properties, let us say mu 1, epsilon 1 and sigma 1, and the second medium has a property of mu 2, epsilon 2 and sigma 2, and for simplicity I have considered what is called as linear isotropic homogeneous media both in the first medium as well as in the second medium. None of these quantities are complex, there is no loss, none of these quantities are matrices, which means anisotropy. Okay. So, we have considered a simple medium. For most of our discussion in this course, this type of media is perfectly okay, and we even have a certain simplification of this media. So, we do not consider non-magnetic media. So, which means that I can put the value of permeability as the same for both medium. Okay. In fact, in many cases we do not even have sigma 2 and sigma 1, but there are a few cases where you would take a, for example, you take a fiber and then coat it with a metal for some sensing application. So, in that case you will have an interface between one dielectric, which is the glass material, and a coating, which is a metallic material or a conductor. Okay. And of course, using a conductor also gives us couple of ideas about how to talk about modes, and that is primarily the interest in which I am introducing this conductor to the discussion. Okay. So, anyway, those things come later on. So, I have an interface up here, and this interface has a normal. What is normal? Normal simply means a line which is perpendicular to the plane of the interface. Okay. So, if I have an interface in this particular form, this corresponds to the normal. So, the direction of the pen here would correspond to the normal. Now, look at it from your side. So, maybe I will turn it around like this. So, you look at it from this side. If you are looking at this plane, right. So, I have I have a set of fingers going this way, which I can call as the x axis. The direction of this pen we would call as the z axis. Okay. And then there is another line, or the another finger, which is a thumb, that is pointed towards you. This would be the y axis. So, I have set up a Cartesian coordinate system in which the interface itself is in the plane which is described by x and y, the normal is along the direction z, and the plane of incidence will be the plane x and z, because light ray would actually come at this particular angle. So, this line or this finger is the one that is depicting a uniform plane wave coming in at an angle theta 1 as measured with respect to this pen. This pen is the normal direction. Okay. So, this is the setup that we have considered, and when I consider such a setup, I am actually interested in knowing how would the following fields change as we go from one medium to another medium. So, let us say we put in all our field quantities with a subscript of 1 to indicate that these are medium 1 values, and then we put the corresponding subscript 2 for second medium. Of course, I know that electric field, magnetic field and all the other field quantities are all vector quantities. So, I do have a vector sign on this. So, on the first medium I have E1, D1, B1 and H1. But if you really look at this, since we have considered only non-magnetic material, B1 is equal to mu naught H1. So, apart from this small scalar value, there is nothing really happening with, or there is nothing really different from B1 and H1. So, we could use one of them to discuss about this so called boundary condition, whereas D1 and E1 are not normally so simple. So, if the medium is perfect dielectric, then this D1 can be written as epsilon 1 E1, where my notation epsilon 1 is actually epsilon 0 epsilon R1. So, instead of writing all the time epsilon 0, I have combined that epsilon 0 with the relative permittivity and called it the total permittivity epsilon 1. Okay. But if the medium happens to be a perfect conductor, then for the perfect conductor sigma would go off to infinity, whereas epsilon would go off to 0. Okay. So, this corresponds to a perfect electric conductor which has no losses. On the other hand, I have a perfect dielectric for which sigma is 0, whereas epsilon goes to whatever the non-zero value. It can't go to infinity, or it does not go to infinity normally. So, a perfect dielectric is one which has a epsilon which is non-zero, but the condition for dielectric is that there is no non-zero sigma value. Okay. So, these are some of the definitions that we have, and for today's module we will be focusing mostly on the perfect electric conductor. Okay. So, what am I interested in? So, after having set up the coordinate system, so maybe this is the coordinate system. So, this is the z axis, this is my x axis, y axis would of course be coming out or going into the page, does not really matter to us. And what I have is a case where there are two fields. So, there is an incident electric field. Okay. So, please note that this is not ray of light, this is actually the field vector itself that we have drawn. Okay. There is a reason for this, it will become very clear once we go to the next part of the course here, or next part of the module here. So, for now just imagine that there is an electric field E1 here, and there is a corresponding electric field E2 in the second medium. Okay. Now, imagine that I am putting up this loop. Okay. I will also label the direction of this loop, the sense of direction around which I have to pass through the loop. So, this loop let us say has a length delta L. So, one half of the loop is lying in the medium 1, the other half of the loop is lying in medium 2. The one that is lying in medium 1 has a height of delta h by 2 here, and the same height in the other medium as well. So, you have to imagine that I have this interface plane, and then I have this interface plane, and then I have this line which is delta L long, and then it plunges on to the second medium. Okay. The total height of this one is delta h, goes down at delta L again, and then comes back up to complete the loop. If you have looked at it carefully, the direction of the sense is that this is along x direction, whereas in the other loop it is along minus x direction. So, it does not really matter which way you take, but you have to be consistent with whatever you take. Okay. So, you can't take both delta L to be positive, it does not really go that way. Okay. Now, what am I going to do with these equations with this picture? Well, I know that integral closed loop integral of E is actually given by minus integral of del B del T dot ds. Okay. What is the ds that we are considering? That is the surface element or the surface area which is actually created by this loop, okay, which is enclosed by this loop, and of course, this surface area has to be open, whereas the loop here on which we are integrating the electric field has to be closed. Okay. So, writing this left hand side with whatever the electric field that I have, I first notice that, or I first note that this electric field can be broken up into two parts. One part will be along the delta L axis or the x axis or the tangential component as we would call it, and the other component will be perpendicular to it, it would be along the z axis, right. And in this dl expression, I am only interested in the horizontal component. There is a reason why that will be true, I will show you in a minute, because if I write down the left hand side, what I have is ET1, where T stands for the tangential component and 1 of course stands for the medium 1. I have ET1 delta L which is along the x axis here, then I have plus En1 delta h by 2, then I have En2 delta h by 2, correct. I have En2 delta h by 2 minus Et2 delta L. Why is it minus? Because the delta L senses are different in the medium 1 and medium 2, correct. So, this is what I have, and then I have minus En1 or rather En2 delta h by 2 minus En1 delta h by 2. Clearly, these cancel out and leaving the left hand side simply as Et1 minus Et2 times delta L. What about the right hand side? Well, for the right hand side we have the surface area, and the surface area that we are considering actually has a total surface area of delta L times delta H, and then you have a certain magnetic field changes that are happening in this particular loop, right. So, if I have the magnetic field, then I need to know what the corresponding magnetic field, the sense of direction of ds will be along the y axis in this case. So, I need to know del By by del T in the two regions of course, right. So, I need to know with a minus sign as well. So, this is from the right hand side of this expression, and what I do now is that I take the limit of delta H going to 0. So, which means that I have this loop and I am basically going to make this loop hug this x axis or the plane of interface very tightly, okay, so that delta H goes off to 0. As delta H goes to 0 and we also assume that the B fields are going to be finite everywhere, the right hand side will completely be equal to 0, and then leaving the left hand side where delta L is non-zero, the only condition that can be satisfied here or the only conclusion that is possible is that ET1 equals ET2, which is tangential electric field equals tangential electric field on the second medium as well. So, this is regardless of whether this medium is dielectric, that medium is conductor. For example, if I have a perfect dielectric medium and a perfect electric conductor, this condition of ET1 equals ET2 simply means on the interface plane ET1 itself will be equal to 0. Why? Because ET2 is already equal to 0 by definition of a perfect electric conductor. So, a perfect electric conductor cannot sustain electromagnetic fields inside it. So, clearly in that case ET2 will be 0, which also means that on the surface ET1 will also be equal to 0. I will leave the discussion of other boundary conditions, okay, but I will just mention those boundary conditions. B1n equals B2n, indicating that in medium 1 the normal component is the same as medium 2 normal component. For D it is slightly different, D1n minus D2n, okay, will be equal to rho s. Again, do not worry about the signs here, whether it is minus or plus, they are actually determined by the kind of problem that you are looking at, okay. The signs depend on whether the charge is positive or negative, but for our consideration as of now, D1n minus D2n corresponds to the difference in the normal D components, and that difference in the normal D components should be exactly equal to the surface charge that is contained in that particular surface, okay. So, you can do this or you can obtain this equation by applying Gauss's law to the two medium situation that we have discussed. I have not done so. There is a tangential magnetic field condition which says that the difference in the tangential field components from medium 1 and medium 2 should be equal to the surface current sheet, okay. So, this is the surface current sheet and this is the surface charge density, okay. So, the discussion of these boundary conditions is nicely summarized in the textbooks that I have suggested. So, please take a look at them. I am not going to derive it, but just to complete whatever that we have been writing, we have E1t equals E2t all the time, no problem whatever the medium are, B1n is equal to B2n all the time, but the D field and H field are discontinuous by the exact amount of surface charge density that can be present and surface current sheet that is possible, okay. It turns out that in most of the course, I mean in most of the modules on the course, we do not really bother with the normal conditions, okay. So, we are only interested in the tangential conditions, and even here we are most of the times fortunate because we will not be considering the perfect electric conductor interfacing with a perfect dielectric. Most of the times we are interested in PD1 and PD2, where PD1 is perfect dielectric in medium 1, PD2 is perfect dielectric in medium 2. So, these are the boundary conditions that are necessary for us to investigate the phenomenon that we have described at the beginning of the module, okay. So, let us specialize to a very interesting case, okay. This case happens to be an interface between a perfect dielectric and a perfect electric conductor, okay. And then I have a normal here which of course will be along the z axis and this one will be along the x axis. This is my interface, let me just indicate that this is the interface that I have considered. And now what I consider is not an electric field, I actually consider a wave propagating along the direction of z in medium 1, okay. So, let us say the medium 1 has a certain refractive index or equivalently the relative permittivity. PEC of course simply means that sigma is equal to infinity or sigma is set to infinity, okay. So, I have a wave here. So, this is wave whose electric field is oriented along the x direction. So, I have an electric field along x direction. Of course, I have a magnetic field in the y direction, and this subscript of I indicates that I am considering the incident medium. Okay. So, clearly if you look at the interface, EXI happens to be that of a tangential component. Okay. If I write down the expression for EXI will be a function of z, of course. So, we have some incident amplitude, and then I have e power minus j k z I times z, right. This is the uniform plane wave that we have considered, which is propagating along the plus z axis, and this is there in the medium 1, right. So, this wave keeps on propagating, approaches and approaches the interface. Now, what happens at the interface? Clearly there is no electric field in the second medium. So, whatever that must happen at the interface plane z equal to 0, leaving me or leaving us with the condition that EOI will be equal to 0, correct. If I go back to this expression, substitute z equal to 0, the exponential term will be 1, and then you are requiring that the total tangential electric field hitting the perfect dielectric be actually equal to 0. If that condition is imposed, then it also turns out that EOI itself is 0, that is incident amplitude itself is 0, which means fields are 0 everywhere. This is not a very helpful situation. So, the only way we can reconcile with non-zero wave propagating, right. So, non-zero wave propagating and hitting the perfect electric conductor is that there is a reflected wave. So, there is a wave which is reflected back, okay, and the reflected wave propagates in the direction which is opposite to the incident wave. I am going to assume that the reflected electric field will be in the same direction, whereas the magnetic field will be in the opposite direction. So, I will have minus h by r, okay. Because EXR is given by EOR, which is the amplitude of the reflected field, but this is propagating in the other direction, right. So, it is propagating in the minus z direction. So, I have KZR times z, okay, where KZI is equal to the free space K0 times square root of mu naught epsilon R1, and similarly KZR will also be equal to K0 times mu naught epsilon R1, because these two are actually in the same medium. So, K depends only on the medium properties, not the direction of propagation. So, now the total condition that I actually have is that EXI plus EXR must be equal to 0 at the interface z equal to 0, which clearly gives me EOR equals minus EOI. So, if you are at some particular distance and then look at the total electric field, the total electric field in this case in the medium 1 will be equal to minus 2 EOI, let us say, and then sine of Kz times z, where Kz is a simple notation for representing both Kzi and Kzr. Now, this condition makes sense because at z equal to 0, the electric field actually goes to 0, and after that the electric field would actually increase, go to 0, increase, go to 0, and so on. So, this is how the electric field gets reflected from a perfect electric conductor. We will postpone the discussion of perfect electric conductor to some other module where it is really required when we talk about the modes. For now, thank you very much.